Is the skin is visible now? Hello?
Yes, sir.
Okay. Am I audible clearly?
Yes, sir.
Yes,
Yes.
sir. Yes.
Okay. Okay. Let's start. So what we have seen in case of this sprocket joint, spigot and sprocket joint, we have seen that how to start our design, and till now what we have seen is the various formulas by means of which we can calculate dimensions of the spigot. And now we are going to start to design the sprocket. Now in case of sprocket, already we have seen the sketch of this sprocket. With this joint, we have started from the rod dimensions, and later on we have calculated dimensions of the spigot, and now we are going to see how to calculate the dimension of this sprocket. Now this sprocket, inside which this spigot is going to insert, and we are going to put this quarter pin, and hence it is able to take the tensile load. That is what the concept is of this joint. And this joint is used to handle the tensile load. Now, as we have seen all these things, and we are going to start to find the dimensions of sprocket. Okay. In case of this socket, when we are going to find the dimensions, out of that already we have described in the detailed drawing of this socket that what dimensions we have given to this socket. That first of all, we are going to see the outer diameter, that diameter of spigot, that is the inner diameter of the socket. Then the outer diameter of the socket, that we are going to calculate. And most important thing is that is C, that is nothing but the dimension of the socket from the quarter pin, that is this dimension, because this dimension is very important. Now here you can see this C is the dimension which we are going to consider, that from this quarter pin up to the end of this socket, this length is important because it is directly sustaining the tensile load, and this quarter may apply its all tensile load on this area. So this distance is very important. Am I clear to you? Hello? Anyone can give
Yes, sir.
answer. Okay, yeah. So that
Yes,
C,
sir.
right. C dimension is very important, and that we are going to calculate with the dimensions of that socket. Now, here we are going to calculate all these dimensions, and later on we are going to check whether that stresses which are generated other than the stress which we are going to calculate, which we are going to consider, that whether that stresses are within the limit or not. If they are within the limit, then we are going to consider that the design is safe. Let me clear you once again that when we are going to consider the stress to design these components, it means that already we have decided what the factor of safety we are going to use for this component. Directly SYT or SUT, that is ultimate tensile strength or yield strength, we are not going to consider in the design in formulas. We are going to calculate allowable tensile stress, allowable shear stress, allowable crushing stress, allowable compression stress from the material which has been allotted to us. That material properties, that is its yield strength and ultimate tensile strength, that we are going to know first, and later on we are going to calculate the design stresses, and that design stresses are we are going to check whether they are in within the limit or not. Okay, so first of all we are going to consider the tensile failure of socket. So when we are going to apply tensile load on the socket, then there may be direct shear. That is nothing but because of the tension, when we are going to apply tensile load, it may elongate, because directly we are going to apply tensile load on that socket, and we are going to consider that it is directly going to elongate. So within the elastic limit, If the elongation is there, then we are going to consider it as a shape. And if it goes beyond the elastic limit, beyond our the stress which we have decided for the tensile stress, then our value of the stress which we are going to decide for the tensile stress, then we are going to consider it as a the material is going to get failed, that component is going to get failed. So the when tensile load is applied, here you can see when tensile load, this black arrow is showing that tensile load is applied. From the other side also we are going to apply same sort of tensile load. Okay, but who is going to apply it? That the sprocket which you are going to insert in that, and that is going to apply the tensile load. So here when we are going to apply tensile load, then there may be possibility that the shear may occur here. That is nothing but directly it is trying to cut out that portion. So here also that same tensile stress will be generated, but we are not going to consider this region. Are you going to see? So let me take pen. If we are going to consider this region, if you consider this region, this also can be considered for the calculation if you want to calculate the dimension of this. But specifically we are going to consider this region. Why? Because if you observe, this is solid one and this is hollow. So which part will be more weak or weaker? That is this part. Even also we are going to make slot also here, this slot. So this is going to make this component as a weaker than the this area or this side of the socket. So we have to consider the weaker area, and if that weaker area is safe, then automatically the strong area will be also safe, because this is what solid one, and here we have made the slot, and also we have made one cavity in which we are going to insert the sprocket. Okay, so this part we are going to consider for the design first, and if we are going to apply tensile load on this, then how it will sustain that tensile stress, whether this red area is able to sustain that tensile load or not, that we are going to calculate, that we are going to check, and according to that we are going to decide what will be the dimensions of this socket. Okay, so first of all we are knowing that this D1 is the diameter, outer diameter. Okay, this outer diameter we have considered in detailed drawing, we have seen it. This is D1. Then this inner part, this inner dimension, this we have considered as a D2. And if you are going to draw its front view, it is looking like this. Also, we have made the slot, this to insert the quarter pin. So this we have considered as a T1. Sorry, T, not T1. T1 is the this length. This we have considered as a T1. Sorry, this as a C, C. And T1 we have considered as a polar dimension of sprocket. This C we have considered. This as a T. This is the inner diameter D2, and this as the outer diameter D1. So how much area which is sustaining this applied load at this plane which we have drawn, in this plane, this red area is going to sustain all the tensile load which is applied on this socket. So that much area we have to consider, because when we are going to calculate the stress, at that time the tensile stress sigma T is equal to tensile force which is applied divided by the cross section area which is sustaining that tensile force. So in this case, this red area is going to sustain that tensile force, and this P is the force which is applied. So we have applied tensile force as a P, and this red area as a sustaining area of this tensile force, and that's why this sigma T are the tensile stress which is our tensile stresses which are generated in that area. So when we are going to calculate this tensile stress from the data which we have given, that is material properties, that is SYT and SUT. Now here in this case, we are going to use ductile materials for all design of this joint. So we are going to consider that SYT as a yield strength, and that strength is the limiting strength. From that, we are going to calculate the design stress by considering the factor of safety. And once we do all this calculation, then that value we are going to consider here as a sigma T. That is the allowable tensile stress in that socket, in this socket. Everywhere that will be the allowable tensile stress. Now, once we are able to find out this, then our job is that how much force it can sustain. See, in exam, they may ask to design this quarter joint for given load, for given specific load, okay, by giving the various properties of material. They might have given that what the value of SYT is, that is ultimate tensile strength is, what the value of yield strength is, and from that you have to consider, and also they have mentioned what the factor of safety you have to consider, or what will be the range of factor of safety. That well-defined problem will be there in exam. Otherwise, that open-ended problems are there in which just they are going to mention that design a quarter joint for sustaining or for the application. For the application, they are going to specify the application, okay, for joining a trailer to the tractor. So we have to consider, we have to collect all the data from design data book or from the previous experience, that how much tensile load has to be considered. Before that, we have to consider that what will the maximum limit of that trolley that it can carry the load. So from that load, we have to calculate the tensile force. And again, we have to decide which material we can use for that. The material which is available readily in the market, that material you have to choose. All these things we have to do when we are going to consider the open-ended problems. Such type of problems are there, but they are not at UG level. So when you are doing actual design, then also lot of work has been done. That's why previous data is available, and from that data you can start your design. So if you want to design such type of quarter joints, definitely already huge data is available, and from that data, from that experience, you can just calculate the dimensions. Now here also we are considering the same thing, and in the exam, the problem statement will be specified that what will be the capacity of that quarter joint, what are the properties of that material, then what will be the range of factor of safety, then what will remain, that remaining values are only the dimensions. So we have to calculate the dimensions of that quarter joint, okay. Such type of problems will be there in exam. Here also, now we are going to convert this formula of this tensile stress, that is sigma T is equal to tensile force divided by cross-section area. Just we are going to rewrite it as a P is equal to, that is what will be the load carrying capacity of that joint. What we have done, that this cross-sectional area we have taken to the other side, hence this tensile stress is area. Now, while we are going to calculate this cross-sectional area, then we have to consider the area which is sustaining this tensile force. Now, this shaded area, that area we have to calculate. Okay, definitely that will not be the pi by 4 d1 square, because if you are going to consider the pi by 4 d1 square, this inner part is hollow. Also, there is slot for the quarter. So this area has to be subtracted from the area which you are going to calculate. So this pi by 4 d1 square, which is the whole area, we have to subtract this area here. Whether it is possible to have some other color for the pen. Okay. So if you are going to consider this area, which we have to subtract this area, so definitely that will be equal to pi by 4 d2 square, pi by 4 d2 square. Okay, so we can take this pi by 4 as a common,
and that will become d1 square minus d2 square. Okay. So once you have calculated this area, is it sufficient that we have calculated all this area which is sustaining the tensile force? No. Here we have created one slot also. So just we have to subtract this slot. So how much that slot area is? So this is upper side slot area and this is lower side slot area. So how we can calculate it? We know that this thickness of this slot is T. But what is this dimension? What we can consider for this dimension? Also, we have to consider this dimension. So this dimension, if you want to calculate, simply what we can do, that d1 minus d2, that means this much length and this much length, automatically we are going to get if you are going to subtract d2 from d1. Okay, so both these lengths are considered, multiplied by t, that will be this area plus this area. Okay, now we can consider that this total is the area which is going to sustain the tensile force, and this area is resisting to this force, applied force, and is not allowing that force to yield that material. Getting me? And if this area is not sufficient to sustain this load, then definitely yielding will start. So if you want to calculate this P, then this total area multiplied by tensile stress. Now here the tensile stress is allowable tensile stress, right? So in this case, now we can calculate some values like d1 in terms of T. Yet we have not decided what the thickness of quarter is, because we have not designed that quarter. We have not considered what will be the stresses which are generating in that quarter. So T will remain as it is. In previous lecture also we have seen that T yet has not calculated. For the spigot also we have calculated some dimensions in terms of T. Okay. But here we can put the value of this D2, because D2 is how much? That is outer diameter of that spigot. That already which we have calculated in the previous lecture. That is here. This outer diameter of spigot we have calculated. Okay. Various dimensions while we have calculated for this spigot, that we have calculated it. So that value we can put, and we can calculate this D1 in terms of T. Okay. When we are knowing sigma T, that is allowable tensile stress value. Getting? Or vice versa, if you are knowing force, then we can calculate what will be the tensile stress which will be generated in that shaded area. Getting? So by this means we can calculate this D1. Now next part is that from this equation diameter D1 can be calculated. Okay. Again there is a quadratic equation. It will become quadratic equation. Okay. So we have to calculate how that quadratic formula can be solved. Okay. At the time of example, while we are solving the examples, then we are going to calculate that dimensions. Okay. So remaining dimensions which we have to calculate are the C part, that is nothing but this much dimension. Okay, that dimension we have to calculate. Also, we have to calculate the D4, that is nothing but this diameter. Let me show which diameter I am talking about. Diameter of this collar, that is from this point up to this point. Let me draw one line up to this. So this diameter we have considered as a D4. Now this D4 has to be calculated. Okay, and also we have to calculate this C. Now D4 and C can be calculated with the empirical formulas. These empirical formulas we can use for calculating D4. D4 is 2.4 of D. D means the diameter of rod. That already we have started our design from the calculating diameter of rod. Okay, this diameter, that is the diameter of rod. This is the D diameter. Okay, so in terms of D, we can calculate with the empirical formula. Is diameter of the outer collar of socket, and also C, that is nothing but the part which is after the quarter of that socket. But that is only not sufficient. We are going to consider that what will be the crushing for that failure. Also, we are going to consider what will be the shearing failure of this uh, socket. So first of all, we will consider the crushing. Crushing is nothing but this quarter pin is going to apply force on this part, and it is trying to push out in this direction. Also, this area is not allowing that shearing or yielding. That's why here at this region, they are going to apply force on each other. And that's why crushing will be operated or crushing will be generated here. And that crushing is nothing but compressive stress. That is for small region area which we are going to consider. On that area, if you are going to apply, if you are going to push your two hands, two palms with each other, then whatever may be the thing which is happening on the palm, that we are going to call as a crushing. Okay. Also, you can just slightly rotate your palms on each other. That is also called as crushing. Okay. So this crushing type of stress will be generated over there, and that we have to check that as good as we are going to consider it as a compressive stress. Okay. So the area which is undergoing for the crushing, that area is nothing but this much area, this area which we have calculated. Okay. Now let me clear all these things and let me show you which area about which I am talking. Okay, I am talking about this area because here crushing is applied and this area. So this area will undergo for the crushing, that is nothing but the compression, because they are going to apply force, that two parts, that is quarter and the socket, they are pushing to each other in the opposite direction. That's why this crushing will be occurring. So that area we have to consider. That area is nothing but this diameter minus this diameter. Okay, this is D4, this is D2. Okay, so this D4 minus D2 multiplied by whatever may be the thickness of this quarter. Okay, that is thickness of quarter, D4 minus D2 multiplied by crushing stress. If you want to calculate this crushing stress, this formula will become sigma C is equal to crushing, that is nothing but we are going to consider as a compression only. Sigma C is equal to force divided by area. Area is what? D4 minus D2 multiply with T, that is the thickness of water. Okay, so this sigma C value, that is the allowable crushing stress or allowable compression stress, is equal to force divided by area. So just we are going to take this area to this side and we have calculated P. P is equal to area multiplied by stress. Okay, P again, this is the permissible or sustainable force by this quarter joint. Okay, till now let me ask, do you have any doubt? Anybody of you?
No, sir.
Okay. Is it going well? Anybody of you?
Yes, sir. Yes.
Because I have received some feedback that, yes, what? Are you getting it?
Yes, sir. Almost.
Yes, sir.
Almost, okay. If you have any doubt at any junction of time, you can just ask me what is your doubt, okay? What do you have not understand, so that we can just clear that doubt and later on we can go further. Because see, as we are going to conduct this online lecture, you are not in front of me. You are not going to look at the board, and we are not knowing actually what things are happening. Just you have to imagine, and I'm trying to explain it as much as it is possible. Okay. And again, if you have any doubt, then just you ask. Yes, huh? Is there anybody who is in doubt? Uh, Please explain how to calculate D4 again. Okay. Once again, just to have to explain how to calculate D4. Now see, D4 is actually the dimension of collar. That is the diameter of that collar. Here, this is the diameter of that collar. This collar we have considered. Now, while we have calculated this dimensions of this socket, that is nothing but this outer diameter and inner diameter we have calculated. Okay. So already we have calculated this inner diameter while we have designed this socket. Now, sorry, spigot. But now what we are going to calculate is the outer diameter of this socket. Already we are knowing this inner diameter. We have just calculated this outer diameter. Okay, with the help of tensile stress. Now, when we are going to consider this collar, at that time, this collar we have not considered as the for sustaining part of any type of stress, because here this is the weakest part. This part you have removed. Also, you have removed this part. Also, you have removed this inner area. Then also this remaining red area is able to sustain that tensile stress. Then definitely this solid area will be able to sustain that tensile stress. So we don't have to bother about it. Just we are going to see that what will be the this external diameter or this collar diameter. Then in that case, why we have provided this collar again? Because when we are going to insert this pivot, then that pin which you are going to insert here has to be restrict, okay, its motion. So we have considered this collar. Now this collar is, or collar diameter is calculated by means of just one empirical formula, and that empirical formula that has come because of the previous experience of designers from design data book, that this formula we are going to consider. Okay, one can go for calculating of that dimension with the help of his experience also. That is nothing but he can try as a diameter equal to D1 only. Then he can slightly increase that diameter as D1 multiplied by something quantity, that is 1.2, 1.3, 1.4, 1.5 likewise. And he goes on checking that whether that quarter joint is able to sustain that stress or not. And all these things are done by means of calculation first, and later on by manufacturing that joint, actual tests are conducted on that. And if that tests are, or test results are positive, then we are going to take this as a diameter. Likewise, by doing all experiments, this value has calculated by designers, and it has included in design data book as the empirical formula, as the empirical relation for calculating of the D4. Hope you have understood it. Sir, how that formulae are for the crushing failure of socket is derived. Okay, how that formula is derived for the crushing stress. Now, see, this crushing stress is equal to force divided by area. Am I clear? Now, how much force is applied? That all this joint is going to sustain this P force. That is the P is the tensile force. Okay, everywhere at any point this force P is applied on this quarter joint, not more than that, not less than that. Okay, so when we are going to apply this tensile load, everywhere we have to consider that this tensile load is sustained, is passed by means of this rod to this got, then afterwards it will go to the quarter, then afterwards it will go to the socket. Okay, and this socket is going to transfer this load to the other end of that socket. Okay, that's why this much load is applied. So force divided by area. Now area, which area is sustaining this crushing? This much length plus this much length. Okay, multiplied by its thickness. So how much thickness is there for the quarter? This much thickness. Okay, that means this area is going to sustain that crushing force. So this area above which force is there, force divided by this area will be the value of crushing stress. That's why here we have calculated as force divided by that area which is sustaining that crushing force. Okay, will be the crushing stress. So just what I have done is that we have taken, we want to calculate P, that's why P will be here only. Divided by area was there, that we have taken to the other side, so it will become multiply. So area multiplied by stress. Have you understood? Deshpande. Okay. So can we go further? Yes. Anybody? Do you have any doubt now?
Yes, sir.
Yes, sir.
Do you have doubt? You can write comment on in comment box also. Have you understood? Hello? Am I audible?
Yes, sir. Yes, sir.
Yeah. Okay. Can we go? Okay. Can we go further? Sushant is saying that yes, you can. Okay. So we'll go to the next slide.
Yes, sir.
Okay. Okay. So this crushing failure of socket is calculated by considering the crushing stress. Okay. And from that, we are going to calculate this sigma C using the equation and check whether it is in safe limit or not. This sigma C we are not going to use for calculating any dimension. See, in the above formula already we have calculated D4, already we have calculated this D1. Okay, sorry, D2. So already we have calculated it. T yet we have not find. T will remain as it is. And just we are going to calculate whether this sigma C, that crushing stress value, is within the limit or not. Okay. We have to just going to check it, this sigma C value. Getting in terms of P again. I should not forget it. That T yet it has not calculated. Then once you check that crushing stresses are within the limit, next thing we are going to consider that there might be possibility that the quarter which we are going to insert here in this slot, this quarter which we are going to insert here, it may pull out all this region like this. Okay, if this quarter is inserted and if this part is very weak, then there might be possibility that these two volumes may come out and this joint will get failed. Right? So how it will be coming out? By means of shearing, direct shearing. Okay, and that failure may occur. So what we have to do? That we have to check whether this area, that red area which has mentioned here, is capable to sustain the shear. It is not allowing to shear out. If this quarter joint is very strong and this part is very weak, then it may get shear out. Okay. So we have to check that whether that shear stresses are within the elastic limit or not, or within the limit, what the value of shear stress which we have considered, that value is sustaining or not by means of this area. That we have to calculate. Okay. So what will happen if the share is going to occur? Now see here, this area, that shaded area, okay, hatching area, that area is gets shared out. Here you can see clearly that area. But little consideration is there whether this much only that red part is going to share out, or opposite part is also there, opposite to this volume rectangles. So opposite part will also get shear out. Okay, that means this is not this red is not only area, but opposite to that red area is also undergoing to the shear. So while we are going to calculating this area which is sharing, we have to take care that we have to consider total area which is going to shear out. Okay, force is going to remain same. So this tensile force is going to remain same. So shear stress tau is equal to shear force divided by the cross section area. Here I have mentioned as a 2, because if we are going to calculate this red area, then opposite to the red part there is again another area which is undergoing for the shear. Getting me? So it is easy to calculate this red area and doubling it, which is going to shear out. Are you getting me? Am I clear? Anybody? Take your own time for getting these points, for visualizing the things. If you have any doubt while considering this area, please ask me. I'll repeat it once again. Okay. So what the thing is that this quarter is very strong, and as we are going to apply tensile force in this direction, okay, this quarter will get pulled out because this pivot is trying to pull this quarter with this force P. Okay, so if this area is weak, it will get shear out, this upper and lower, because it is hollow one. We are talking about only spigot. Sorry, this socket. Okay, spigot is inserted here. This socket is hollow one, and this much area is only area which is going to shear out if the shear stress will exceed than its limit. Getting me? So we are going to calculate the shear stress tau. Now this tau value can be calculated from the material property, that S y t divided by 2 is the allowable shear force. But when we are going to consider the design shear force, that is the value which we are going to consider here, this is allowable. But when we are going to consider this tau is again the tau which we have calculated as allowable divided by factor of safety which we are going to consider. Now we are knowing what the factor of safety is. Okay, so you have to consider this factor of safety, and then afterwards this tau will be calculated, which we are going to consider here. That is the design shear stress. Okay, once you have calculated this design shear stress, if you are knowing the force which has to be sustained, then only part will remain as we have to calculate the cross section area. Okay, now this equation I am going to rewrite as tau is equal to P divided by A. I am going to use for the cross section area. Okay, so 2 multiplied by area. This equation in terms of P will become P is equal to area. This area we are going to take to this side. Okay, so it will become this total quantity which we are going to take on this side. So this quantity multiplied by tau. So this quantity multiplied by tau. How we have calculated this quantity now? That is the question. 2 we need not to be calculated because we are going to consider this area and opposite area. So that's why we are going to use 2. then how to calculate this red area? Now one can understand that if you are going to take the cross section of this, then D4 is the outer diameter, that is, this is the D4, and from here we have to consider up to this point, that is the outer diameter of this socket. Okay, is D2. This is D2. If you are subtracting this D2 from this D4, that is this D4 and this is D2. If you are subtracting this D2 from this D4, we are going to get this length plus this length also. Am I right? Okay. So once you have got this length, only thing is that we have to calculate this length. This vertical length multiplied by this horizontal length. This vertical length multiplied by this horizontal length will be the area, right? So we are not going to consider double time this C. So this vertical length plus this vertical length, that is D4 minus D2 multiplied by this horizontal one, that is D4 minus D2, here it is, you can see here, multiplied by C, that is the horizontal dimension of this collar. This will be the area, and we are going to double it as this first side and this side. That's why we are going to double it. Am I right? So we are going to get this area, which is sustaining shear, multiplied by shear stress value, that will be the value of force which will be sustained. Okay, so here shear area we have calculated as D4 minus D2. This D4 minus D2 multiplied by C, multiplied by C. Is it clear to all of you? Hello?
Yes, sir. Yes, sir.
Okay. If you do have any doubt, you are free to ask. Now, if you don't have any doubt, let me ask one question to you. In this formulae, which quantity we can find out? P is equal to, in bracket, 2 multiplied by D4 minus D2, bracket complete, multiplied by C, other bracket complete, multiplied by tau. Which dimension we can find out from this formula?
C.
C, right? We can find out C because already we have decided what will be the P, that is force which is applied. Somebody has written in comment also. Sushant, yes, C. Because already we have calculated P, that is the force which is applied on that quarter joint. Also from this formula, that is from the material property, we are going to calculate allowable or design shear stress. Also already we have calculated what will be the D4 by means of empirical formula. Also we have calculated D2. Let it in terms of T. Let it in terms of T. Okay. So we have calculated this T2. Only remaining quantity is C. It may comes in terms of T. Let it be as it is. Okay. While we are solving problems, again we will see how to calculate first that T and later on how to use it in the various formulas. Okay. But we'll go step by step while we are learning all this design. So let that T as it is. Okay. Now, very good. We have calculated C from this formula, and here we have done calculation up to our satisfaction for this socket. Okay. So we are going to use this socket, and just I have written this formula which I have derived in previous slide, that this P is equal to twice of the area, that is D4 minus D2 multiplied by C multiplied by the allowable shear stress tau. Okay. Now, once we have done this, then we have calculated all dimensions of that socket. Now we concentrate on the quarter P. When we are going to insert that spigot in this socket, we are going to insert the quarter in that slot which has provided for the quarter. Okay, and this quarter is going to sustain the load. Now, if we are going to make this socket strong to sustain that P, if we are going to make this pivot strong to sustain this P, now we'll concentrate on this pin, because this pin is the locker one, because this is going to lock these two parts, that is socket and spigot. Okay, so this pin is also undergoing to various stresses. Now you can just list out which stresses will be induced in that quarter pin. Can you just give me name of one stress which may get induced in this quarter? You can write in comment box. Hurry up. Any one stress. Hello, am I audible to all of you? Hello.
Yes, sir. Yes, you audible.
Okay. Can you give me just one stress which will get induced in that quarter joint? You can imagine all that quarter joint. Okay, let me give overall view of that quarter joint. Yes, this is overall view of this quarter joint. Now this, when we are going to insert this pin, so which stress may get induced in this pin? Now this is upper part, that is socket. This is inner part, spigot. This is pulling in this direction, and this is pulling in opposite direction. So here also you can consider this socket is trying to pull out all these things to each side. This spigot is trying to pull out all the things to each side. He is trying to pull, he is also trying to pull, and this is one who is going to connect all these two parts together. So what type of stress may get induced in this part? Yes. Someone has, yes, shear stress. Sonone has written shear stress. Also Sushant has written as shear. Then Ubay has written as a shear stress, right? It may undergo for the shear, because if you are going to consider this as a chalk which has inserted in the slot which has provided in that, and definitely if we make this socket of plastic, suppose plastic is the material which we are going to use, and this pivot also we have manufactured from the plastic, and here if you inserted it as a chalk, then there might be possibility that this plastic part, as plastic is having more strength than the material from which we are going to manufacture chalk. Okay, definitely this chalk will get break in three pieces. Here it will get break, here also it will get break, so it will get shear out, right? So this part will go with this socket to this side, and this middle part will go with the this pivot to the pivot side, definitely, right? So now you are becoming designer. Okay. If see in all this part, what is important is that we should able to understand which type of stress may get induced in that part. Okay, that is the first thing. And second thing is that which area is going to sustain that stress. That is important. If you are able to just visualize which stress, the stress is equal to force divided by area. Then if you are able to visualize which area is encountered by that type of stress, then definitely you will be able to calculate the dimensions of that area. And that is what is in this all subject, all our course. Okay, calculating area, calculating dimensions. Getting me? So you have to just visualize stress and area. Now this is fourth step of this total design, and that we can consider as a last step also, because there are three parts which we have to, no, not three, four parts, because we have considered that rod one, okay, then sprocket second, then sorry, spigot second, then the socket is the third one, and this quarter as a fourth one. So these four parts are there which are assembled together and this joint is formed. So this is the last one part which we are going to design, that is nothing but we are going to calculate the dimensions. So already we are knowing that T is the thickness of that quarter, B is the width of that quarter. Already we have defined it, okay, in the previous slides. Again, I'm going to define it in the next slide also. Here, this is the width, okay, this is the total length. This length we are going to consider for the quarter pin, okay, width of the quarter pin, and this is the thickness T, which we are going to consider for the quarter pin, okay. So this quarter pin we are going to design now. Now, based on previous experience and design data book, we can calculate T as 0.31 of diameter of that rod. At this point, we have calculated this T. Okay. Now, if we calculate this T, then remaining dimensions are there. That is width of that quarter pin and length of that quarter pin. That we have to find out. Okay. Just here we have decided what will be the thickness of this quarter pin. All other dimensions which we have calculated in terms of T, that now we can convert at its actual values. That will be numbers now. So put this T value in the all above calculations which we have done and just calculate the numbers or dimensions of that respective parts. That is, calculate the diameter of that inner diameter and outer diameter of that socket. Also, you calculate the diameter, that is only one diameter is there, of that spigot. Calculate the diameter of collar of that spigot. Calculate the diameter of collar of socket. Okay. Also, you calculate C, that is the thickness of that collar. Wherever you have kept that T as it is, just put that value of T and calculate that values. Okay. So once we have decided this thickness, now you may ask that if we are going to decide that thickness, why you have not decided it at earlier stage? In this case, I have not calculated, I have not used this formula at the starting of this design because we have to go through the procedures. We have to just find out, we should know, we should able to imagine which type of stress and which area. So that is only two imaginations which we have to do in all this design process. We are not bothering about that T, we are not bothering any dimension. We are just concentrating on which type of stress may get induced because of this action of applying force P, and which area will be encountered by that stress. Now, there may be tensile stress, there may be shear stress, there may be compressive, there may be crushing and compressive, they are same as we are going to consider. Okay. So these stresses we have to just imagine and area which will be encountered by the stress. That's why we have not calculated this T in the beginning only. Okay. So let's consider that T has calculated. Now we have calculated T and we are going further for calculation of other dimensions of that quarter. Now, already you have mentioned that this pin will get shear. Yes, definitely that will be the major stresses which will be induced in that pin, because we are going to manufacture this pin of some ductile material. Okay, and definitely that ductile material will start to yield when we are going to apply the tensile force. Okay, and most of the cases the shear will occur in this pin at this junction here and here. Now, once you are able to imagine stress, then just we have to calculate which area will be encountered by the stress. Now, while we are calculating area, this is the red area which is encountered by the shear stress. Not only this, because this shear is not occurring at the one place, it is occurring at the two places. Okay, so we have to just double this area. Forget about this slanting edge. As we have manufactured this quarter with some taper, forget about that taper. Okay, just we're not going to consider that taper. That taper is very small, and just for the calculation, we are going to neglect that taper, and we are going to consider this red area is just as a double because of the double shear. Okay, so here I have written that double shear will be occurring in the quarter. So we'll see what will the formulae which by means of which we can calculate the shear stresses. So when we are going to consider this double shear in the quarter, then the shear stress tau is equal to the shear force divided by cross section area. And as the area we are going to double, that's why 2 is used there. That is the only thing. Okay, so we'll try to find out what will be the cross section area, and we will calculate this formulae in terms of P. Just we want to calculate the shear force, that is the same as the tensile force or force which is applied on that joint. Okay, so this is P. We have taken this area to the other side, this cross section area multiplied by 2, and shear stress as it is as a tau. Now, when we are going to consider this formulae, that is P is equal to 2 multiplied by B is the thickness of this quarter multiplied by T, because when we are going to calculate the area, at that time we have to consider this B as a width and this T as a thickness. Okay, so B multiplied by T will be the area, this red area, and just we are going to double it. You can imagine that area in this section or in this section of the quarter. Here also this value will be T and this value will be B. Okay, so that area we have calculated, B multiplied by T, just double it, and shear stress, allowable shear stress for this pin material, not allowable, design shear stress for this pin material. This design shear stress is also calculated from the allowable shear stress. The allowable shear stress is equal to SYT, that is the yield strength which is given to the material, because in actual problem they are providing us this yield strength only. We have to calculate this allowable stress by considering the factor of safety. Sorry, here from directly we are not going to calculate factor of safety. Here we are going to write 2, then this will be the factor of safety, okay, which we are going to use the term. So allowable shear stress is calculated from SYT divided by 2. Okay, then design shear stress are calculated tau as a tau A allowable divided by factor of safety. Okay, by means of this, again already we have calculated T by empirical formulae. Tau you have calculated now here. P you are knowing how much force has to be sustained by that quarter joint. Then value of B can be calculated from this formula. Okay, we have calculated T, that is the thickness of that quarter pin. We have calculated width of that quarter pin. Length is calculated by means of empirical formulae. Okay, I'll give that empirical formulae in one table. The second thing is that if that pin is not get shear, then what will happen to this pin? Will it get bent? Because this part is pulling to this side and this part, upper part and lower part is pulling to this side. There might be possibility that this pin may get bent like this. It will bend like this. So these bending stresses will be generated, right? So while we are going to consider this bending stress, then this bending stresses are calculated. Now here we are going to consider these bending stresses. And we are going to use that formula m by I is equal to f by y is equal to e by r, because we are knowing that in case of this beam, simply supported beam, if you are going to calculate sigma b, that sigma b is calculated by means of this formula, that m by I, bending moment divided by cross section area, that is moment of inertia of that cross section, is equal to e by r. R is the radius of curvature of that bending. R, okay, is equal to sigma e by e by I is equal to e by r is equal to y. Y is the distance of that layer from the middle layer. Okay, if you are going to consider the cross section of that bending part, this is the neutral axis, and you are going to consider this as a y. Okay, and for this cross section only, you are going to calculate I. Then bending moment is calculated by means of force multiplied by distance at which the force is applied. From this formula, you are going to calculate sigma b, okay, allowable bending stress. Now, little consideration. Let me ask one question here. Truly, what the bending stress will be? In true sense, what do we mean by bending stress? Is it the separate as a tensile is separated from the compression? Then tensile and compression is separated by shear. Shear stress is different at all from the compression stress. Compression stresses are different at all from the tensile stresses. And these three stresses are separately, can be clearly visualized and observed in any component. Okay. So likewise, do you feel that bending is also at all different? It has a different properties and all different structure, or it is coming in that above mentioned stress only, that is tensile, compression or shear. In terms of tensile, compression and shear, we can describe what the bending is or bending stresses are. Anybody of you can write in comment whether that bending stress is different from tensile, compression and shear, or truly physically that stresses are nothing but only tensile and compression, and combining together it is going to become bending. Yes, am I audible? Koi?
Yes,
Yes,
sir.
sir.
Okay, then can anybody of you tell me what the bending stress means? Omkar, Omkar Mashelkar. Hello? Omkar Mashelkar. Are you there? Once again, I repeat, Omkar. Harshal Nakter has joined. Okay. Let me ask one question to Harshal. Harshal, are you able to listen me? Hello? Yes, okay. Can you unmute yourself, Harshal? Why? Okay. Have you understood all the things which were studied in this lecture? Okay, related with that network issue. But have you understood the things? Little bit. So what you have not understood? You are free to ask. I will repeat it for you. Hello, Harshal. What you have not understood? Because it is very important that you should attend the lectures. Yes. So what part you have not understood from this previous lecture or all the slides which we have started right from morning 10? Can you write in comment? Okay, we will move further. So can anybody of you tell me what the bending stress means? Really, whether it is combination of tensile, compressive and shear, or it is a separate type of stress which combination of tensile and compression stress. Yes, Akash has given answer. Anybody else? Anybody else? I just want to listen from you. Sushant Jadhav has told that it is same. I'm eager to listen you. Amol Mari. Can you just unmute yourself? Amol. Sir, can short. Sonal, just you want to repeat this slide. Am I right?
Yes, sir.
Okay, I'll repeat it. See, we have calculated this shear stress. Second thing is that if it is not shearing, if it is not shearing out, then there may be possibility of bending. It will get bent because this part, which is held by means of this socket pivot, and this upper part, which is held by means of this socket, this upper part is pulled with the socket to this side, and this inner part with this pivot is pulled to this side. This is the condition. So if it is not getting shear, then it is possible that it will get bent like this. Okay. So we have to calculate the bending stress. Now here we are calculating just this bending stress. Now bending stresses are calculated by means of M by I is equal to F. F means stress, sigma T, sigma B actually, not T. Sigma bending divided by Y, and E by R. Young's modulus divided by area of this curvature, radius of this curvature. Okay. By means of this formula, we are going to calculate this value of sigma B, and that we are going to put here. Now forget about how this formula is derived and all that. Okay. Just we are going to check this. Just we are going to elaborate this, because it will take separate derivative and derivations. That is long derivation, which is not actually scope of our course. Okay. And if you want, I will explain it to the next lecture, how this formula is derived. But here just I want to ask one question, that how this sigma B is calculated by means of this formula is calculated. Okay. I want to ask that whether this sigma B is different from the tensile or compression. Now you have given answer that it is just combination of tensile and compression, because when the bending is occurring, what will happen to this upper layer? This upper layer, it will get, yes,
It is under tension.
compression. If it is bending, huh? See, I will draw this. This is lower part. It is in tension, and this will be in compression.
Compression.
Right. Okay. So here we can consider this as a sigma C as a compressive stresses, and here we can consider as a sigma T as a tensile stress. So when we are going to say this compressive and tensile stress, this tensile stress. Okay. When we are going to consider this compressive and tensile stress, just we have to check that whether it is in the limit of design stresses, whether that compressive and tensile stresses are within the limit. And
Screen is
by combining these,
not visible.
screen is not visible. Just wait.
Sir, it is visible.
Is it visible now? Hello?
Yes, sir.
Visible.
Okay. Everybody is
Visible,
able
sir.
to, yes, able to see the screen? Hello? Are you able to see the screen?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Okay.
Bending failure of quarter.
Yeah. Okay.
Yes, sir.
Right. Okay. Okay. Now, from this bending stress, we are going to calculate this formula in terms of width of that quarter pin. This B is equal to under root of 3P. Okay, P is the tensile force. Then T is the thickness of that quarter pin. Sigma B is the allowable bending stress. Okay, you can consider it as a maximum compressive or maximum tensile. In most of the case, you can consider this sigma B as a tensile value, limiting tensile stress value. Okay, then D2 is the diameter which we have considered for the socket. D4 is the outer diameter of that collar of that socket. Minus D2 is again inner diameter of that socket divided by 6. Okay, this D2 divided by 4. Now this is calculated from the empirical relation, that not empirical, quadratic equation which has generated because of this m by I is equal to f by y is equal to sigma b by r, sigma b by y. Now just we have to check that value of b, which we are going to calculate by means of this formula, is less than the value which we are calculated by means of this formula. Here also we are going to calculate this b. If suppose this b is coming as a 10 centimeter, then if this b is coming as a 9 centimeter, we are going to consider that this b is within the limit. But if this value of b is coming as a 11 centimeter, then this 11 centimeter is considered as a value of b, though from this shear we are going to get value as a 10 millimeter. But if it is coming from this bending formula as a 11 centimeter, then we are going to consider this 11 centimeter as a dimension for this quarter joint, because this quarter will get fail if you are going to consider as a 10 centimeter as a width of this quarter. It will sustain shear stress, but it will get fail in bending. And experience shows that definitely it will not come above, this value will not be exceed than the value which you are going to calculate by means of this formula. But here is the strong stresses which are generated in the quarter rather than bending. Rather than bending, we are going to consider that, are not considered. Experience shows that shear stresses are the more stronger stresses which are generated in that quarter. Okay, so we have calculated all the dimensions of this quarter also. Then what we are going to do is that just I have formulated all these calculations in one sheet only, in one slide only. If you see this table is only sufficient for understanding all the design procedure of this quarter joint. Also, if you are knowing all these formulas, you will be able to find out the dimensions of this quarter joint. Now, one by one, I will repeat it from where we have started design of this quarter joint and where we have ended this design. Okay. So first of all, we'll see that here we have started our design from calculating dimension of rod. That what we have calculated in the dimension of that rod, that is diameter of that rod. Okay. Now, considering which type of stresses, pure tensile stresses in that. This rod will be undergoing for the tensile stress. Okay. So we have considered this criteria as a tensile failure. And hence we have used the formulae as force is equal to cross-sectional area multiplied by stress. Now the stress which we are going to consider here is the design tensile stress. Okay. So this design tensile stress and force, if we are taking from the data which has provided by the examiner or in that example, then we are going to calculate this diameter. This diameter we are going to calculate, that is the diameter of that rod. Okay. So from this point we have started our design. The next part which we have taken for the design is the spigot. Now for this spigot, we have considered various criteria of failure. First of all, we have considered that it will fail in tension. Now which part will get fail in tension? Which is weaker. Okay. So in that, just I will repeat that slide here. It will get fail in tension. Which part is weaker? Definitely this area, because this part is solid area. After this joint, it is also solid. This part is also solid. Okay. That's why, as we are going to make slot here, this slot. That's why this is weaker one. And in this case, what dimensions we have calculated, that we will see in that chart. Okay. But here we are going to consider that failure will occur. And if this here failure is not occurring, definitely failure will not occur at this region also, because this region is solid one, more strong. We have just removed material from here only. That's why it has become weaker. Okay, because less area is sustaining that, and here that area is higher than this area. So, okay. So the tensile failure will occur. Here also we are going to use same formula, that force is equal to cross-sectional area multiplied by stress. Now this cross-sectional area is calculated as pi by 4 d2 square minus whatever may be the slot in that which has provided, that is d2 multiplied by t. Okay. So this area is removed from the total area. That will be the area which is sustaining that tensile stress, multiplied by tensile stress will be the value of sustained tensile force. Now from this, what we have calculated, that we have calculated as a d2, and yet we have not calculated t. Now here we can consider that t. This t, what this t1 is, that is the thickness of collar which we are going to provide to that spigot. Okay. and this D3 is the diameter of that collar. Okay. Then A is the area which is remained after the quarter. Should I again go to the slide where we have described dimensions? See here. This we have considered as a diameter of socket. Here we are going to consider this collar. This collar diameter is D3, which we are going to calculate from this same empirical formula, and this length as a, which we have calculated while we are going to consider that spigot failure in tension. Okay, and also no doubt that we are going to calculate this outer diameter of spigot 2, that is D2. Okay, if possible, I will provide this total PPT to you by providing here the actual picture of that part. Okay, this I will provide the picture of that part in this section, in this column. Okay, so we have calculated this outer diameter of collar, then thickness of that collar, and remaining part A by means of this empirical formulas. That is D3 is equal to 1.5 UD, T1 is equal to 0.45 of D, and A is 0.75 of D. Now don't be get confused in T and T1. T1 is the thickness of collar, T is the thickness of quarter. Okay. Now next we have considered crushing stress as a failure pattern, where the crushing is occurring in between that quarter pin and slot which has provided on the spigot for inserting that quarter pin. Over there is as a this region. Okay. This is the total what we are going to say diameter of that spigot, and this part is undergoing for the crushing stress. So we have considered this as an area. So cross sectional area multiplied by crushing stress. Cross sectional area is this total diameter multiplied by this thickness. Now this diameter we have taken as a length of this slot, okay, and thickness of this slot, width of this slot. Okay. So from this we have calculated as a thickness. We may calculate here because D2 already we have calculated from this formula. Here also you can calculate this thickness. Okay. And if you are knowing the crushing stress value, once you have calculated this thickness, we have to cross check it with this last one. Okay. If it is coming higher, then this thickness will not be considered. I'll repeat. Thickness T is the thickness of that quarter, which you may. Are you able to listen me? Am I audible? Okay.
Yes, sir. Yes, sir.
Right. So by means of this empirical formula, if suppose this T value is coming as a 9, and by means of this formula, if it is coming as a 7, then you don't consider this as a 7. You have to consider always higher value of any component, any dimension. By means of this all formulas, whatever may be the value which you are going to get for the same parameter, which is higher one, that you have to consider. Should I repeat it? I am repeating that from all these formulae, whatever may be the highest value of same parameter, same dimension, which you are getting, that you have to consider for the dimension of that part. Okay. Next, we are going to check the shear failure also for this spigot. And in that shear failure, we have considered that the area which is undergoing for the shear is this much area, this cross-sectional area. Already we have described it in that slide. I'll repeat once again that slide. Here. See, this area. This area will get shear out because of this pin. Okay. So this area, just we have to double it because from both sides shearing is occurring. Okay. So this area we have to calculate. This area will be definitely this length multiplied by this length. So this length is nothing but the diameter of this spigot. Okay. And this length is nothing but A, which we have calculated. A dimension. Okay. So this D multiplied by A and double it. That will be the total shear area. At 2 into A into D2. Okay, that will be the total sheared area. Multiplied by shear stress value, allowable, not allowable, design shear stress value. Okay, is equal to the P which we have calculated. Now, from this formula also, already we have calculated D2. Tau you are knowing, P you are knowing. Just you can cross check that whether this A which you have calculated from this formula is less than this formula. If this value of A is less than value which we have calculated already, then that total component is safe in shear. Okay, by means of shear failure criteria. Here also we are going to calculate this tau value is within the limit or not. If you are going to put this A as it is here, this D2 from this formula as it is here, and P, that is the force which is allowed, force which you have to transfer, then remaining value will be only tau. That tau value we are going to check whether it is in safe region or not, whether it is less than the value which you are going to calculate from the ultimate tensile stress. Okay, so this spigot is designed now. Now next part which we are going to take for the design is the socket. And this socket also we are used different criteria of failure, and from the different criteria we have calculated different dimensions. Now what are that criteria? First criteria which we have used is the tensile failure of that socket. Now this tensile failure is occurred as area multiplied by stress is the force. Okay, so which area will be encountered in the tensile? That area we have calculated as this area, this red area. Okay, how we have calculated this red area? That is D1 minus D2. Okay, first of all we have calculated all this area, that is pi by 4 D1 square. Okay, we have subtracted this hollow part, that is pi by 4 D2 square. Also we have subtracted this region, okay, which is equal to T1 minus D2 multiplied by T. Okay, that means this remaining shaded area which is undergoing, which is sustaining tensile force, tensile stress. So here this is calculated as pi by 4 D1 square minus D2 square minus D1 minus D2 into T. This is the area multiplied by tensile stress, that is design tensile stress, that will be the allowable force which can be transferred by means of this quarter joint rather than with this spigot and socket quarter joint. Now from this formula what we have calculated? We have calculated D1 value, that is the outer diameter of that socket. Then we have calculated D4 by means of this empirical formula. Already we have calculated D2 here with this formula while we are designing the spigot. Okay, so not necessary to calculate this D2 again. We have calculated just D1, this D1 value by means of this formula. Okay, Then D4 we have calculated by means of this empirical formula, that is D4 is what? Diameter of collar of that socket. Also we have used one empirical formula to calculate thickness of that socket as a C. Okay. Once you have calculated these two values, just we are going to check whether that component or that socket which we have designed is safe under crushing failure. So which criteria we are going to use for the failure is the crushing failure. Now, how we are going to calculate that crushing failure? As force is equal to area multiplied by stress. Now here we are going to consider the crushing stresses. Okay, this crushing stresses multiplied by area which is encountered by this crushing, and that area is nothing but area which is there for the socket, this area. This area, this all area up to the end point here. This is undergoing for the crushing. And how this area is calculated? That is this total length multiplied by width. And how much this width is? This width is equal to thickness of that quarter. And how much length is the diameter? This total diameter, which we have calculated for the collar. So this diameter of the collar and thickness of that quarter pin multiplied by the crushing stresses. Okay, so we have considered this crushing stresses, crushing failure for this socket. Next, we have considered as a shear out. This may be possible that this socket get are all part of that socket if they are sustaining tensile and crushing stresses, and if it is weak in shear, then it may get fail in the shear also. So shear stress, when we are going to consider for the failure of criteria, then force is equal to area multiplied by stress. So which area will get shear out? That area we have seen in the slide here. This area will get shear out. How much this area will be? This D4 minus D2. That means length multiplied by width. Width is C. Okay. So D4 minus D2 multiplied by C. And as the double shearing is occurring from the both sides, that's why we have used 2. Okay. Multiplied by design shear stress. Okay. Now this formula, with this formula, we are not going to calculate any dimension. Just we are going to check whether that shear stress value is within permissible limit or not. Okay. So by means of all these criteria, we are going to calculate dimension of the socket. Once you have calculated dimensions of the socket, that is the D1 value, D4 value, C width, then we are going to check whether the crushing stresses are within the limit and whether the shear stresses are within the limit. Okay. Then last part of this design of this total assembly, that is the quarter. That quarter pin which we are going to insert in that slot which has provided for the quarter pin. And for that we are going to use criteria as a shear and bending. Now, first of all, with the help of empirical relationship, we are going to calculate thickness of that quarter. Okay, that thickness is in terms of diameter of rod, that is 0.31 D. Here we are going to find out thickness. Then we are going to check whether the tensile stresses are within the limit. Here it is not tensile stress, it is shear stress. So this will be the tau. Okay, by considering the double shear. Now shear stress is equal to force divided by area. Hence force is equal to will become area multiplied by stress. So which area will get encountered? That is the cross-sectional area of that pin. It will get shear. Okay. But shear is not occurring at one place. It is occurring at two places. This is one and this is 2. That's why we are going to use 2 here. So 2 multiplied by this area, that is its width, multiplied by thickness. Okay, so B into T, and as the double area is there, this one and this one, 2 multiply with shear stress. In this case, we are going to calculate width of that quarter pin. Okay, and once you have calculated this width, then we are going to just check whether that width is able to sustain bending stresses. Now, value of this bending stresses is considered as a one of the principal stress, that is tensile stress we are going to consider, and by means of all these formulas we are going to just calculate B, and if this B is less than the B which we have calculated with this formula, then we are going to consider that it is in safe region. Okay, in this case here it is written that choose higher value of B by comparing these two formulas. Once you have calculated B value with this formula, then compare it with the value which you are going to calculate with the bending. Okay, whichever may be the higher, that you consider as a width of that quarter pin. Okay, so I'm going to provide all this slide also, all slides to you. My request is that once you understood, then just go through this table. That's all. You will be able to solve any question on this quarter joint, any type of. Okay, do you have any question? Yes, do you have any doubt? Hello, am I audible? Parmar, am I audible?
sir.
Am I audible?
Yes, sir. You are audible, sir.
Okay. Just I want to ask, do you have any question?
No, sir. I don't have right now.
Okay, you. Anybody else? You can write in comment if you have any question. Okay, we don't have any question. Further, do you have any
Sir,
question?
please provide class note so we can write in our notebook as soon as
Yeah,
possible.
I will provide all, and that all are in typed format. Okay, that word copy is there, so I will provide that word copy to you. Shortly, I will provide that link to you. Today only, if possible. Today only I will provide that. Okay, next. Who is this? Right now admitted.
No, sir, by mistakenly I have cancelled the meeting.
Okay, no. Now, if you don't have any question, let me take presently. Meanwhile, if you have any question, you can ask. Hello?